Hey gang, another lesson on electric current, and now we have electrical stopping power, the introduction to resistance. Resistance to the flow of current is simply what happens inside of a circuit. Notice in this example, this visual, the current is moving and then it slows it down tremendously in the resistor. So what is resistance? Resistance is a measurement of how strongly an object will oppose the flow of current. You could kind of think of it a little bit like friction, although it's not friction. Okay, depends on four factors. The four factors are something called resistivity. It's specific to the material. The higher it is, the more natural resistance the material has. And you'll find a chart of resistivity in your New York State issued reference tables. The length, how long something is. The longer it is, the more it will oppose the flow of current. That makes sense. The farther you have to move, the harder it is. Cross-sectional area. How big across is it? The wider it is, the more current will allow to pass. Think about a hose. If you're trying to shoot water through a little garden hose versus a fire hose. A big fire hose will allow more water to come through because it has a bigger cross-sectional area. And last but not least, the temperature. If the object is warm, the molecules inside will be bouncing around more, which causes an opposition to current. Remember, we talked about electrons being transferred one to the other by bouncing off of each other. So higher temperature means you're going to get more of that kind of electron drift that we talked about earlier. So how do you remember this? Well, here's the equation. R, resistance, equals rho, that's what that first symbol is here. This symbol means rho, times length over area, where R is resistance, rho, that's a Greek letter, is resistivity, L is length, and A is cross-sectional area. The unit for resistance is the ohm, right? And it's used the Greek symbol omega here to stand for it. All right, let's try a problem. We would like to have conductors that allow current to flow from one place to another very easily. So what would be the ideal conductor? Long or short? Well, the ideal conductor would be short. Shorter conductors have lower resistance because the electrons don't have as far to travel. How about wide or narrow? Well, yes, the wider the conductor would have lower resistance because the electrons have more room to pass. How about hot or cold? Yeah, colder wires have lower resistance because atoms are not as energetic. They don't interfere with the flow of electrons. The ideal conductor has a low resistivity and is short, wide, and cold. Okay, let's try an example problem. Calculate the electrical resistance provided by a piece of copper wire with a length of 1 meter and a cross-sectional area of 0.01 meters squared. Okay, the formula is R equals rho L over A. Substituting values now to solve. The resistivity here, 1.72 times 10 to the negative 8 ohm meters. We got this from your New York State reference tables. We looked up copper. Times 1 meter times 0.01 meters squared. The resistance would be 1.72 times 10 to the negative 6 ohms. Okay, example number 2. What is the composition of a wire that has a resistance of 31.8 ohms if it is 5 times 10 to the 7th meters long and has a cross-sectional area of 0.025 meters squared? Again, the same formula, R equals rho L over A. Substituting values now to solve. Rho is 1.59 times 10 to the minus 8th ohm meters. We look at our reference tables and we see that that is silver wire. That's it, gang. End of show. A little bit on resistance.